What are some of the unsolved problems in quantum mechanics and physics? This is a question from Quora.com. What are the, what is it? Answer basically that question in quantum physics. What is it that we're looking at? We're looking at the basic fundamental things and their energy structures, and how they mess around in energy, What is it? It's a basic particle. What is its behavior? How does it behave? So how does it move? We've answered these questions. How does it get into relationships? There are equations, out there that tell us how it get into relationships. Telling us all these characteristics of it, how much energy it's having. We've answered these questions, and by answering these questions in quantum physics, we have all these amazing things. It's fantastic. We have electricity, we have radio, we have phones. We've moved away from the mechanical. We have electric cars, from the steam engine and from the things, lots of mechanics, stuff. We have artificial intelligence. This is from understanding and solving problems in quantum physics. What is this thing we're looking at? It's going to give us self-driving cars. It's giving us television. It's giving us internet. We are having a relationship right now because we've understood this thing. This small little thing. What is it? We've answered that question. Why does it travel like that? Why does it travel like that? It was a problem. Nobody knew why it travels like that, but we've answered it. We know it travels like that because there's a finer medium underneath, and this finer medium is the ether. We've just identified the ether. It's just been identified, and in time, and ether, that's the end. The ether has nothing to do with quantum physics anymore. That's the end of the particle. It's something else. It's another category of physics, you understand? Because quantum physics is dealing with the fundamental building blocks of this universe, which are the particles. The ether is not a particle. Perhaps everything's made from the ether, but it itself is not a particle. It's a different category of physics, and it's only got one experiment to its name to prove it exists. And we were not even looking for it, But there's still lots of questions to ask, in quantum physics. It's not like it's done, Maybe I would say maybe it's halfway done or slightly half, 45% way done. I was reading people who say, "Oh, we're done with quantum physics." No, we're not done. It's because we haven't asked other questions. Why is there constant energy imbalance in nature? Photons are light. Is an energy regulator. There's too much energy within an atom, and what do we get? We get light. You understand? Just try this experiment, the black body experiment. You heat it up. As you put more energy into the atom, you get light. But this happens naturally, consistently. Let's say this is an atom. This is an atom. Now, there's a nucleus deep inside, and pretend this, and the photons are going around, and all sorts of random manners. Then this photon hits this. There's now too much energy in this atom, and another photon comes out. So we know photons are energy regulators. But why is there always more than enough seemingly energy nature that it's always getting rid of energy. Magnetism. Let's look at magnetism. Magnetism is from charged particles. They are getting extra energy from somewhere that they release, a pair of Khumalons, one North Pole, one South Pole, But these Khumalons are the result of this electron having too much energy. So that charge means it has a direct relationship. We can only say the ether, So it's getting consistent energy to maintain that charge, and consistently it has to keep on releasing these magnets so that it doesn't have too much energy. Just like the atom has to consistently release photons as light hits it, That's how we can see things, Because there's energy is being balanced, and there's this constant energy imbalance. I mean, gravity is another energy imbalance because it's radiating and there's no destruction. Understand? So this is a large body or any body. The gravity is radiating, and we know it's radiating because there are waves. So that means, and we know it's associated with mass. That means every body on this earth, in this universe, be it the earth, be it Mars, Jupiter, the sun, be it Andromeda, black holes, they all have gravity, and they're all radiating this gravity that is attracting stuff, meaning it's got too much energy. This energy is being released as gravity. Some of it has been released as light, some of it has been released as magnetism. But this is energy regulation. Now you're going to say, but the cosmos, the universe is full of stuff like cosmic rays, these ionized particles and neutrinos, but they are from a destructive process. You understand? When we get neutrinos, electrons and neutrons and they smash into each other, then we get neutrinos, we get all sorts of other stuff, like in colliders. Those are destructive. We are talking about natural energy regulators, which is light, photons, magnetism, the Khumalon, gravity, gravitons. Those are it means there's too much energy, and to maintain itself, but the system needs this energy, but it has to consistently release it. You understand? So all charged particles are like that. They'll be releasing consistently. They're getting energy for this charge and releasing it. Why is there always this? And photons. Let's say this hits an atom, another photon comes out. So we've got there's the whys of things. Why does magnetism behave the way it does instead of slightly different or different? Why like that? You understand? Why does an electron behave as it does? Why does it get a charge or quarks, or leptons? Where? You understand? There's so many, the why of it. Why is the gluon like that? We understand it's like that and it keeps things together, but why is it like that? These are fundamental questions that have to be asked. The whys, not the hows. Why is it traveling like that? Why is it like that? Why is an electron like that? Why isn't it slightly bigger, slightly smaller? No, they might seem stupid questions, but they are deep. So there's a long way to go. So there are a lot. We'll probably covered 45% of quantum mechanics because we still got to ask the whys.